So exam 3 is on Friday. And it's up through stresses and beams. And it's cumulative, so remember, there'll be old stuff too. Yeah, I think, so general, flow of stresses and beams. So first, you have to calculate the external loads on the beams. Then the internal loads. And, that can be general. Like I can ask for internal loads for any given value of x as a piecewise function. I could also, if all I'm asking for is stresses at a single point, then you could just calculate this at the one x value. Most likely, since it's a test and I'm trying to test internal loads and stresses in beams, I'll ask for, the full function for the internal loads and then ask for the stresses at a single point or something. But once you calculate the internal loads, okay, so this can be as a function of x or at a specific location. Once you've done that, calculate the stress tensor due to tension and compression. Stress tensor due to, what's the order we usually go? I guess bending next. The stress tensor due to the shear force. And the stress tensor due to the torque. And this is the one where often you'll need to transform your stress tensor from some temporary coordinate system. That's the one I usually call capital X, Y, Z. And then your total stress is just the sum of those. And in a lot of problems, there'll be at least one of those that is 0. So, you can skip that step. And then, formulas. This one comes from sigma xx is equal to T over A. This one comes from sigma xx is equal to negative my over I. The shear force one, tau xy, is equal to negative VQ over IB. And then for the torque, there's two ways you can go about it. In the capital coordinate system, if you have a circular cross section, this can be torque times rho over I sub p, negative, yep. And then if it's a thin-walled tube, this can be torque, negative again, torque over 2 times the thickness times the area of the median. I think that's it. So the kind of questions that occur to me most easily are like, I could have you solve some kind of simple structure to come up with the external loads on a beam, then have you calculate the internal loads, then go from those to calculating the stress at some point, then calculate the principal stresses and the max shear stresses. That's sort of a pretty natural flow that takes into account most of the stuff that we've done. You know, maybe have you draw the stress element or whatever. That's very likely some set of those things will be a question. Any other general questions about the test? Okay, so 7. Fred, have you been to Sambusa King? You should try it. No, I haven't. You should. Okay. Not today. I went there for dinner like a couple days ago because my family's out of town this week, so I can go to more exotic places. I don't have to satisfy 7 and 10-year-olds is the main. Yeah, right. Yeah. All right, so we got a solid steel bar. With a torque that way and a torque this way, and I guess they're equal and opposite. 4,000 Newton meters. The coordinate system is the way that we always use it. The length is 0.8 meters. The radius of the cross section is 3 centimeters. And it doesn't matter what X value you're looking at because all the internal torques are the same. But it says for the cross section, we want to look at, there's a bunch of points. So A B, C, those are all along this line. And then D, E, F, where this angle is 30 degrees, and G, where this angle is 30 degrees. Let's do one that, let's do this point here. It's not one of any of these, but it combines some of the things that these do. So let's do that point that's halfway in between A and G. Okay. All right, so first you have to calculate the internal loads. We already have the external loads. For this to be in equilibrium, this torque has to be 4,000 Newton meters. And so a cut, and it doesn't matter where you cut it, there's a 4,000 Newton meter torque there, and an internal torque there. Moment equation about the x-axis says 4,000 plus the torque is equal to 0. So that internal torque is negative 4,000. Okay, so now we have this. Is this a circular cross section or a thin walled tube? Circular, and I think it's solid. Yeah. It's a circular cross section. So we know we're going to use this formula that says tau capital X capital Y is equal to negative torque times rho over the polar moment of inertia. Torque is negative 4,000. Rho, we're not going a full radius out, we're only going half a radius out, so rho is equal to 0.015 meters. I sub p is pi over 2 times radius to the fourth, so 0.03 to the fourth power. And what do you get for that? 1.0 times 10 to the minus 6 meters to the fourth. So tau, capital X, capital Y, is equal to negative of negative 4,000 times 0.015 divided by 1.0 times 10 to the minus 6. And what do you get for that? 6.0 times 10 to the 7 pascals. Okay, so in our rotated coordinate system, so what we have for a stress tensor in the capital coordinate system is 0, 0. 6.0 times 10 to the 7th, 0. And then symmetry, 0, 0. In pascals. And this is all in a coordinate system oriented like this, where that's the capital Z axis. That's the capital Y axis. And this angle is 30 degrees. We want to rotate it. We want to re-express this tensor in a coordinate system like this, where that's the Z-axis and that's the Y-axis. So what's the rotation it takes to go from the capital to the regular one? Right. Yeah, so you can rotate this clockwise 30 to make it line up there, and then it's 180 from there. So minus 30 plus 180 is 150. And so the rotation matrix is 1, 0, 0, 0, cosine of 150, sine of 150, 0, negative sine of 150, cosine of 150. And then the stress tensor due to torque is just equal to that matrix Q times the capital stress tensor times Q transpose. And I guess all that's happening with this is torque, so that's also equal to our total stress tensor. Any questions about that? Well, actually, in this case, that's a good question. You could just say, in this case, you don't need to. Because since the stress tensor due to torque, the stress due to torque is the only stress on the thing, you could just say, I'm giving my answer in this coordinate system, and that would be okay. But generally, the reason that you have to rotate it is because you've calculated the stress tensors for all your other internal loads using this stress tensor, and you can't add stress tensors until they have the same coordinate system. Just like, you can't add two vectors that are expressed in different coordinate systems. Yeah, I mean, I guess I just did it because force of habit. I just always think of doing it. But in the case where the only stress you have is due to torque, you don't have to rotate. And I suppose also if all you have is stress due to torque and bending, or stress due to bending and or tension, you also don't have to rotate because rotating the coordinate system doesn't affect the x normal components, because both of these two coordinate systems have the same x axis. But I think you might want to just do it because you're going to have to do it sometimes, just stay. Oh, it does? Oh, okay. So then you have to. Okay, yep. And so once you do this to get the stress tensor in the coordinate system that's given, the usual coordinate system, then just find the eigenvalues. That gives you the principal stress tensor, and then you can use that to get the maximum shear stress. Any other questions about that one? Any other homework problems you want me to do?
Which ones will be in the exam? Could you do those?
No, I don't know what they are. Otherwise, I would. Yeah, I'll make it up like Friday during lunch. We could have just sat there forever.
I know. You said you were going to give us half of the solved problem, maybe, and have us
I think that was in dynamics, right? Or was that in this? I can't really think of how I would do that in D form. I mean, I suppose I could do it with like a partly solved structure or something. I guess maybe I could do that. I won't make you do. I won't make you do very. On a 50-minute test, I don't want you to spend 2/3 of the time solving a structure. You know what I mean? So that's eligible to be on there, but most likely not going to be emphasized. Yeah. I'm not sure how I would fit a structure into a 50-minute test. It's not on structures, you know what I mean? So. Yeah, I could maybe make you do something like, I could definitely see myself giving a question like, that would be a surprise. Didn't expect that, did ya? So let's say this is 10,000 newtons per meter. This is 1.5 meters, 1.5 meters. Calculate the internal loads, and then calculate the stress at some point on the cross section at that location or something. That's quite likely, I would say. 80% chance something like that'll be on there. Yeah. Well, the distributed load, yeah, probably distributed load, but that's not 80% chance of a distributed load. It's lower. You can send me, doesn't hurt to send me stuff, if I like it, maybe I'll use it. That'll give you a good advantage on the test. Yeah, if it's really hard. Okay. All right, so I want to do the statically indeterminate torque problem that I set up last time. And I think it looked like this. So there was this bar between these two fixed supports. And there was a torque one way or the other of, I think it was 4,000. Opposite way. Oh, 1,000? So 1,000 Newton meters. And this was 3 meters. And that was 1 meter. And it was a circular cross section. With a radius of 1 centimeter. What are the external loads? Okay. So first we need to do the statics. And in general, you'll look at a problem and, you know, for a complicated problem, you don't know from just looking at it whether it's statically determinate or not. You just come up with the equations, and if you have enough equations, you're done. And if you don't, you need to go on and use the deformation stuff. So first, the statics. So a free body diagram. The only stuff going on is moments, couples about the x-axis. So we have this 1,000 Newton meter torque here. And then we have reaction torques at these two ends. I'll call this torque A and torque B. And the moment equation about the x-axis says torque A plus torque B plus 1,000 is equal to 0, or these two together are equal to negative 1,000. So that's one useful equation, two variables. So we know we're going to have to find more equations, and we'll just call that equation star and move on. So now what we have to do is calculate the internal torques. How many cuts do we have to make in this? 2, because we have the point torque. So our first cut is valid for x's between 0 and 3. We have this torque TA, and we haven't gotten to this 1,000 Newton meter torque yet. And then we have the internal torque. So the moment equation about the x-axis says TA plus T is equal to 0. Or in other words, whatever TA is, the internal torque there is the opposite. Okay, so this is valid only for x values between 0 and 3. And then the second cut is for x's between 3 and 4. This time we do have that 1,000 Newton meter torque. And we do have this TA still. We just haven't gone all the way to the other external torque, the other reaction torque. And so we have the internal torque T. And the moment equation about the x-axis says TA plus 1,000 plus T is equal to 0. So this time T is equal to negative TA minus 1,000. And that's valid for x values between 3 and 4. And now we want to use these expressions for the internal torque to calculate the angle of twist that we get for the entire beam. By the way, so we have this expression T why did we have to go through all this to come up with t as a function of TA? Why didn't we just leave that as a variable t? Yeah, exactly. I mean, in a way, you can think of these as more constrained equations. We started out with the variables TA, T, and TB. We can't do anything about those, but we don't want to bring in any more variables or we're going to need even more equations. And that's why we want to express everything that we have here in terms of the variables we already have, yeah. And now the final restriction says, since this is a fixed support, we don't know what the angle of twist is at any of these points in between the two supports, but we know that there's no angle of twist between this and this point, okay? It can be twisted here, anywhere in between, but it has to go back by the time it gets here to that starting twist, because those can't slide on the wall. Okay, so the total angle of twist over the whole length is 0. And we have piecewise constant internal torque, so we're going to use this formula that says the angle of twist is equal to the torque, the internal torque on the first part, times the length of the first part over G times I sub P, and then plus the internal torque on the second part times the length on the second part divided by G times I sub P. I said also when I set this problem up that this is a kind of steel that has a Young's modulus of 200 times 10 to the 9 pascals and a Poisson's ratio of 0.25. We can use those to calculate G. G is equal to E over 2 times the quantity 1 plus nu. So that's 200 times 10 to the 9th divided by 2.5. And what do you get for that? Eight times 10 to the 8th. Oh, yeah, right. 8.0 times 10 to the 10th, right. And that's still in pascals. And then we need the polar moment of inertia. For a circular cross section, that's pi over 2 times radius to the 4th. So pi over 2 times 0.01 to the 4th. So 1.57 times 10 to the minus 8. Yes. I got it going on today. I got one right in dynamics. This is meters to the 4th. So the total angle of twist is negative TA times 3 divided, oh, that's not even going to matter anyways. None of this stuff is going to matter. Nothing really matters. Because this is all going to cancel out. The 3 is going to matter, and the torques are going to matter, but not the... plus negative TA minus 1,000 times 1 divided by G I sub P. And the reason those won't matter is because we have 0 angle of twist. So we can multiply both sides by G times I sub P. And so you get minus 4 P sub A is equal to positive 1,000 and so P sub A is equal to negative 250 Newton meters. Now plug that back into equation star, the thing we got from the statics. That's a terrible star. And you get negative 250 plus TB is equal to negative 1,000. So T sub B is equal to negative 750. And so the external load that's closer to the, the reaction load that's closer to the applied load has to take up more of that load. And that's, you see that always. Any questions about that?
How would you have to figure out the angle of rotation at the torque applied?
That's a good question. So, well, the way you would do that is, so we have we know the internal torques everywhere. So if you plotted this out, here's 3, here's 4. We know that we have a internal torque of positive 250 on the first part. And on the second part, we have 250, so minus 750. Okay, so that's what a graph of the internal torques looks like. And so you'd have to, decide whether you want to calculate the angle of, the angle of twist. So it won't matter either way. Okay, so the angle of twist is the internal torque times the length divided by G I sub P. And we're just going to do it over those first 3 meters. So this is going to be 250 times the length of 3 divided by 8 times 10 to the 10th times 1.57 times 10 to the 8th minus 8th. And could someone calculate that? .597. 0.597 radians, which is a pretty big angle. But so what that says is it goes through an angle of like 35 degrees or something.
34.2.
Yeah. 34.2 degrees is the angle of twist right where that external load is applied. And then it goes back to an angle of twist of 0 at the 2 attachment points.
So then to choose, you always just start from the left. So
Yeah, if you started from the right, you'd have to just think about the signs more, you know. But you could do that too. You know, yeah, I would just always go from the left. I mean, you could figure out how the signs work if you thought about it a little, but I would just always go from the left, and then you don't really have to think about it. Any other questions? Okay, let's stop. So test on Friday.